Nth order homogeneous differential equation, and then we have y1, y2, all the way up to yn. There's n of them. It matches the order. There are n linearly independent functions that satisfy the differential equation. That's what the fundamental set is called, or that's what the fundamental set is. Then your general solution to the differential equation is a linear combination of those linearly independent functions. And it's all kinds of linear stuff here. I feel like we're in linear algebra. So this is what we saw from last time. We talked about linear independence, and we talked about the Wronskian as a way to check for linear independence and all that stuff. All right, so today we're going to introduce the non-homogeneous part. This is still section 1. We didn't quite finish it. So we'll introduce this part, and then we'll just say the solution, just so we can get the form of the solution for a non-homogeneous differential equation. So here we have a non-homogeneous linear nth order differential equation, and they're saying that y sub p is a function that satisfies this. So the definition is, the vocabulary that we will be using is that y sub p is a particular solution. So in our conversations we'll be saying, oh, we need to find a particular solution. That just means that's a function that would satisfy this differential equation. Function that would satisfy this non-homogeneous differential equation. Yeah?
Is there ever more than one not including the trivial ones?
If there was another particular solution, it would be linearly dependent to this. So there's only one linearly independent particular solution. So now we paste it all together, and pasting seems to be the superposition principle. You just put it on top of that. So if you remember this from the previous page, this is the solution to your homogeneous differential equation. To find the general solution for your non-homogeneous differential equation, you would include the exact solution for the homogeneous differential equation, and then you would tack on the particular solution. This is your general solution. General solution for the homogeneous and then you add on your particular solution. And all of a sudden you have a solution, you have a general solution to your non-homogeneous differential equation. Okay? Which is cool. Superposition principle says we can compartmentalize. We can break down these tasks to smaller tasks. And then all we have to do is add it all together in the end. Okay? So that's what that's saying. And then they have a summary. This is a superposition principle. This is basically what I have written down. Oh, particular solutions can be written like this too. Oh, so Evan, maybe I should rephrase my answer, correct myself. So if you have a particular solution, no, I think it's still true. Yeah, so it's a particular solution. So what they're saying here, another superposition principle, is that if you have a sum or difference of terms in the non-homogeneous part, then you can just find solutions for each one of those terms and then add it together for your particular solution. Okay? So the idea is that if you have a non-homogeneous differential equation, linear, let's just say every time we talk about a differential equation here, it's a linear differential equation. So anytime you have a non-homogeneous differential equation, you have to solve for the homogeneous differential equation first, and then you have to find a particular solution to the non-homogeneous. And then if your non-homogeneous differential equation has a right-hand side that has more than one term, you could just take each of those terms separately to find a particular solution.
It's just the wording is a particular solution, which implies that there are multiple different.
Yeah, well, it's a particular solution, but like I said, the other particular solutions would be linearly dependent.
Right, but it would have to be some of those. Yeah.
Well, no, this is saying you have your right-hand side has more than one term.
Right.
Then you can find a particular solution for the first term, and then you can redo your. Yeah, it'll be the same thing. All right. So there's one more picture I want to add on here, then we can actually start doing problems to try to bring all these theoretical ideas to light. And the general summary is that, well, we've been talking about it. If you have a homogeneous differential equation, you get your fundamental set for the homogeneous differential equation, the fundamental set. And then for a non-homogeneous differential equation, you get the homogeneous portion, and then you add on your particular solution. Okay? So that's the general summary of section 4.1. And then let's get to 4.2 now. Okay? So now we're going to try to solve for these things. And the first thing that they discuss is the idea of reducing or coming up with another solution. Because if you have a second order differential equation and you happen to have one solution already, then how are you going to find your other solution? Because you should be expecting two solutions for a second order. So the main idea here is to find another solution if you already have one. So suppose y1 is a solution to a second order differential equation, then y equals u sub x, or u of x times y sub 1 is also a solution. And then what you could do is you can plug that information into the differential equation and then solve for u. And then piece it together. All right. Let's do an example. Maybe we should start with number 1. So, looking ahead, let's take some notes here. We have to assume that this is a second order, this is a second order linear, homogeneous differential equation. So we should expect our fundamental set to contain 2 functions, right? So we can call those 2 functions y1 and y2. And then in the end, our general solution would be y equals c1 times y1 of x plus c2 times y2. Okay? We don't need to find a particular solution because this is not a non-homogeneous differential equation. So this is what we want to go for, which is what we want to find. So we need 2 things. We need a second function. We need our second function to be linearly independent from the first function. So these are the ideas that we got from last time. So now let's actually go through the work to see if we can find our second solution. We have our y1 is equal to e to the 2x, right? So what we want to do is we want to make a substitution by saying y of x equals u of x times y1 of x. I just wrote that thing over. U of x times e to the 2x. Maybe I needed more space for this problem. So, what do we want to do? Well, according to this, we need to find y double prime and y prime. So, let's find y prime. That's the derivative. U is a function of x. So this is a product of 2 functions. And then we need to find the double prime. So we have a couple of products. So it's u double prime of x e to the 2x plus u prime of x e to the 2x times 2. So that's a product rule for the first. Now let's do a product rule for a second one. There's a 2 out there, so maybe I'll attach that to the u. 2u prime of x times e to the 2x plus 2u e to the 2x times 2. Looks a bit messy. Let's see if we can simplify it a little bit. There's only one u prime here, or u double prime. There is 2u prime times e to the x, and I'll underline that so I can combine these 2 terms, right? 2 plus 2 is 4. I guess I should have factored out an e to the 2x first. So let's do that. E to the 2x. I'm going to drop the u prime of x business. I'll just say u prime, or u double prime plus 4u prime plus 4u. Okay. So now I will take this information here. This is my y double prime, and this is my y prime over here. I'll simplify that a little bit. And this is my original y. So I want to put all that into this differential equation and see what I can get. So what do we have? Y double prime first. Let's have e to the 2x, u double prime plus 4u prime plus 4u minus 4 times, and then I have y prime and I'll switch the order here a little bit. This will just be 2 u times e to the 2x, and then my original y was u times e to the 2x. That's it, equals 0. All right, we got the components here. This is y double prime, actually including this. This is y prime. This is y. And they all have an e to the 2x, so I can just take that out and divide it out. That'll just get rid of all that. So let me just cross it out from here. So pretend I factored it all out, and then I divided it out. So what do we have? Let's gather all the u squareds. There's only one u squared, or u, not u squared, the u double primes. There's only one of those. So that's gone. Let's gather the u primes. There's 2 of those. That's 4 minus 4. That disappear, right? So that's gone. Let's gather the u's. I got 4 minus 8.
Why is that? We look at your original in 4y.
4y?
Yeah, 4y. Okay. Okay, I was wondering where the u came from. That's right up there.
Is that okay?
Yeah, well, how do you decide that y of x is equal to u of x plus y1 of x because of our general form?
Oh, that's the suggestion that they had here. Make the substitution. All right, where were we? Everything else disappears? Is that
Yeah.
correct?
It does.
Hmm. Well, we need to find u. So if you had something more complicated here, you could probably use a substitution, but there's nothing really to do here except to solve for u. How do you solve for u? U prime is a constant, and then integrate again. U is equal to cx plus another c. Actually, these constants aren't going to be that significant, so you can just say this is equal to x. Wow, does that mean this is our solution? Wait, what's our second solution again? It's our second solution is that it has to be, no, the first one times this. So y2 should equal to x times e to the 2x. That's the u sub x that we found times the first solution that we had. Oh, I hope this is correct. Yeah. How do we know if this is the correct solution? I suppose we can look in the back of the book. Right. This is a differential equation. We found the answer, so we can always plug it back in, right? Which is what you're supposed to do to check your answer. Let's check our answer. So let's check if this is a solution to the differential equation. Again, the differential equation is y double prime minus 4y prime plus 4y. So we check that by, well, we need to take a couple of derivatives, it looks like. Y prime is, oh, another product rule. Derivative of the first times the second plus the first times the derivative of the second. And then we need the second derivative as well. So this is just 2e to the 2x, and then the product rule for this one. Derivative of the first times the second plus the first times the derivative of the second. So there's a 2 there, and then an extra 2 that comes down. So this is my second derivative. Now let's put that in to y double prime minus 4y prime plus 4y, and let's see if that's going to equal to 0. So this is 2e to the 2x plus 2e to the 2x plus, oh, I should have combined that first. That would have saved a little bit. 4e to the 2x plus 4xe to the 2x. So let's try that again. This is 4e to the 2x plus 4xe to the 2x. That's double prime. The prime is e to the 2x plus 2xe to the 2x. And then the original function is xe to the 2x. All right, let's see if this works out. We can again factor out an e to the 2x. So let me just scratch all those out. That's too much scratching. Maybe I'll just draw a line through it. So we can factor that out. So e to the 2x factored out. And then I have all the terms with an x. I got a 4x minus 4x minus 8x. I should write this down. 4x minus 8x plus 4x. And then the terms without the x, I have a plus 4 in the beginning here. This one, minus 4. And then there's no other terms over there. Oh, there it goes. So this thing turns out to be 0. This is 0. The whole thing is 0. So it is a solution to a differential equation. Phew, good thing. It worked.
So would the general solution to this guy be...
Oh, yeah. So our general solution, y is going to be equal to, what's our first solution? So we'll multiply that by a constant times e to the 2x. And then our second solution, x e to the 2x. And again, multiply that by another constant. There you go. Two-parameter family for a second-order differential equation. Bam. Cool, huh?
So do you need to start with one solution for it?
It'd be nice if you had one solution in the beginning, because chances are they're not gonna give you one solution. You have to find both of them. Yeah.
I feel like I know what you're saying because I took circuit analysis.
Okay.
And we talked about solution, the general solution for second order.
Yeah. Yeah. Yeah, so if you've seen this, you know that solutions are going to be like combinations of e to the whatever. But let's keep it a surprise. What? Say it again?
When do we get to that?
Now, I think. Well, I don't know. Let me check my notes. There's more examples we can do. Yeah, we probably should do another example.
So what if they don't give us the solution right off the bat?
Then maybe you need to take circuit analysis. Oh, wait, you learned that in this class too. So we'll take a look at it.
So that's later.
That's like in 10 minutes. Keeping you in suspense, Alan. All right, what should we do? Use the method of reduction to find the second solution. Let's try to do another one. I don't know, 17, 18, 19, 20.
19 looks like it's size.
Oh, wait, that's, we have to find a particular solution here, too.
Oh, yeah, those are
All right, let's do another one from up here first. Nah, let's skip over that. This is what are we gonna do? 19, you said?
Let's do 19 and let's,
All right.
let's do that.
That's what we're looking for. Something terrible.
Get the terrible ones out of the way.
Wait, they didn't talk much about. Oh, I think we're missing something here. Well, let's I don't know if we can solve for non-homogeneous differential equations yet.
Wouldn't we need to solve
The homogeneous part, right?
equation first? Yeah.
Is that what they're asking for?
I think that's what the instructions said.
So solutions, use a method of reduction to find a second solution for the homogeneous and a particular solution. All right, well, let's see if we can find a particular solution. All right, let's first need to find y2 to complete our fundamental solution, or fundamental set. So let's work that out. So we're going to focus on the differential equation y double prime minus 3y prime plus 2y equal to 0. We're going to focus on the homogeneous portion first. And then we know that y1 is equal to e to the x is one solution. So we're going to assume that y2, well, let's just say y, is going to equal to u times e to the x. So u is going to be a function that we're going to find, and then we're going to multiply this by. So we need the first and second derivatives. Y prime is going to be u prime e to the x plus u e to the x. And y double prime, we need the derivative of this, so it's going to be u double prime e to the x plus u e to the x u prime. So that's the derivative of the first term. The derivative of the second term is going to be u prime e to the x plus u e to the x. So it looks like, well, let me just not write e to the x so much here. U double prime plus 2u prime plus u. All right? So some product rules. And then we're going to plug it into this differential equation now. We got y double prime minus 3y prime plus 2y equals 0. Put those values in. E to the x, u double prime plus 2 u prime plus u, and then 3 times e to the x, u prime plus u, and then e to the x times u. All right, we can factor out an e to the x again. And then what do we have left? We have u double prime. This is 2 minus 3, that's negative 1, minus u prime. And then the u's, there's 1 here, 1 minus 3 is negative 2, and then negative 2 plus 2 is 0. That's it. Now, by the way, this is always going to end up without a u. Think about that, because u is a solution. Anyways, because we need to solve for u to figure out what this other solution is, our second solution. All right, so they suggested, it's not quite as easy as it was before, so they suggested that we do another substitution. Yeah?
I was going to say, yeah, you could maybe
Well, they call it W, I think. So we'll let W. Yeah. So if we let W equal to U prime, then W prime equals U double prime. And then if we do that substitution here, by the way, we can get rid of e to the x, right? Because it's just 0. So we have W prime minus W equals 0. So now we have a linear differential equation.
The solution to this is u x, isn't it?
Again? Yeah, this is the old W prime equals W. I mean, if this was more complicated, you would do the integrating factors and all that stuff, but hell, if it's something you know, then you can just do it.
Yeah.
So this is just e to the x. Wait, that's W. W equals e to the x. And so we need U, right? So this is U prime. So that means that U it's also equal to e to the x. Nah, we'll save the constants for later. Yeah, because our solution, remember, our second solution would be y is equal to u, e to the x, times the first solution. So a general solution for the homogeneous differential equation is going to be given by y equals c1 e to the x plus c2 e to the 2x. Okay? So now, for the particular solution, how are you supposed to find a particular solution?
Look at me.
Add, just add that 5 e to the 3x. Oh, I don't know.
It's something to do with 5.
Has something to do with it.
It's something to do with it.
Yeah.
That was last section though. That was so.
Yeah.
Basically forever.
So,
Wait, so this general solution, it's like, we're trying to label these as we go on, write out steps.
mhm.
And this concludes this is the
Homogeneous.
homogeneous general solution.
Yeah. So now we need a particular solution. So we're going to take a stab at a particular solution. Maybe, yeah, let y sub p. But we need to make a guess of what y sub p should equal to.
How many, that 5 e to 3x is there?
Not,
Do we know if there's more than one of them?
well, I would guess that it's going to be some constant times e to the 3x. And so the idea is that your particular solution, we should probably kind of match the right-hand side, right?
Can we go back to the thing where it said what you do with the YP, whatever that was?
Is it this one?
Yeah, that.
What's that say? Yeah, I don't think it says anything significant here.
No.
Here they're assuming that you already have particular solutions.
Well, we have in the form of line 12, right? That's given to us. Or is that not right?
Yeah, it is.
So it's given to us in that form. Then how do we know what our I value is?
Well, in this case, there's only one I value because we only have one term in their right-hand side. We only have this term on the right-hand side.
What would it look like if there was more than?
If there was more than one term, then that would be, the first term would be your I1, I is equal to 1, and then your second term would be I is equal to 2. And then you would find them separately.
In this case, we'd have like a 6e to the x.
It'd be like
No.
was adding another term, like 5e to the 3x plus x squared or something.
So any function. Okay.
Just adding another
Yeah.
function of x.
Yeah, so if there was another function, or even exponential or polynomial or anything, then you would find a particular solution separately. So I'm just going to guess that a particular solution might look something like this. There's probably another way to find it according to this section, but this is like 2 sections from now. So let's just solve for this. The y sub p is a solution to the non-homogeneous differential equation, which includes the prime and the double prime. So I'm probably going to want to take the derivatives and then plug it back into the differential equation. So the original non-homogeneous differential equation now. So non-homogeneous dE, which was y double prime minus 3y prime plus 2y equals 5e to the 3x. So that's my dE. I'm going to put the y double prime in, and then I'm going to put the y prime in, and then I'm going to put the y in. And we can see that they all have an e to the 3x that would cancel out with e to 3x. We have essentially a 9a minus 9a plus 2a. And then so what's a equal to? So it looks like our particular solution y sub p is going to be 5/2 e to the 3x. So we have our general solution to the homogeneous differential equation. Now we can write our general solution to the original non-homogeneous differential equation. And that will be the solution to the homogeneous part plus the particular solution. Well, if it's an exponential function raised to some constant times the power, you'll just match that. If it's a polynomial, like x squared, you would match it with a x squared plus b x plus c. It has like a little flavor of the partial fraction things that we used to do. But there are recipes for those for certain functions, and we're generally going to be dealing with functions that we know of. If it's the sine, then it'll be a combination of sine and cosine, because sine and cosines in our discussions here are going to be together. They're always paired up. All right, so here's our general solution to our original differential equation. So maybe we'll put a star here in finding the particular solutions, because there's going to be a whole section on doing that. And I don't know exactly what their technique was supposed to be for this section in finding the particular solution, but we'll take a look at it later. Okay. Any questions? If you guys didn't like Calc 2, then this must be horrible. All that means is that you should practice. Practice, practice, practice. All right. We're going to go to the next section, and for this, we're going to simplify our problem a little bit more and not just deal with linear differential equations, but deal with linear differential equations where the coefficients are all constants. And it turns out there's a lot of different kinds of physics and engineering problems that rely on these types of differential equations, including circuits, including the spring problems, all based on this business. So it's worth studying, and it's fun to do. So our focus now is going to be on homogeneous differential equations with constant coefficients. And the process for doing this, and we'll see that this will become like a recipe algorithm, is that we're going to assume that your solution is an exponential function. Y is equal to e to some power. And the power, we'll just refer to the power as a variable for the moment. And what we're going to do is we're going to come up with an equation that we'll call the auxiliary equation. To help us find the roots of this, and that helps us find m. And we'll see that. Let's take the example that we did. What was the last differential equation that we had? Let's just make it homogeneous.
Y double prime minus 3y prime plus 2y.
So let's consider the homogeneous portion. And let's use this technique where we assume that a solution is going to be some exponential function. And then we'll plug all that stuff into here and see what we come up with. So based on our assumption that y is equal to e to the mx, and then we're going to need the second and first derivatives. And each time you take the derivative, you increase by a factor of m. And so our second derivative will have m squared e to the mx minus 3 times our first derivative is m e to the mx. And we have 2y, which is just e to the mx. Now, when you take all the m's out, or e's, the exponential functions out, And then you can actually divide it out because it's never 0, so you can actually get rid of it. You have m squared minus 3m plus 2, which is kind of like the original differential equation, right? So this is called your auxiliary equation. Solve for m. You can do the, what do you call it? Quadratic formula, or you can factor, and if it's easy enough to factor, why not do that, right? M plus 2, no, minus, minus on both. Minus 2, m minus 1. So what are your roots? M equals 2, m equals 1. And your solutions are supposed to be e to that power. So your y 1 is going to be e to the 1 times x. Your y2 is going to be e to the 2 times x, which was the solutions that we got. Well, e to the x was given, but we found e to the 2x when we did that reduction technique, right? So that checks out. These are exactly what we were looking for. But now, instead of having, somebody asked, what if you're not given, Alan asked, what if you're not given the first solution? And here we found the two solutions without having anything from the beginning. Evan?
Is randomly approved solutions of that form?
Yeah, you can assume that you have another solution, and then somewhere along the line you'll run into a contradiction.
So
Sorry, I just kind of waved my hands on that question. But
I'm going to assume that this doesn't always work, because otherwise why the hell would we do that last thing? This is so much easier.
this is way easier, huh?
Yeah.
As long as it's constant coefficients.
When we did the last thing, this is so much quicker.
What was the first one that we had? Y double prime.
Okay.
Minus 4y? 4y prime plus 4? 4y. Okay? So let's jump to the auxiliary equation. Can you jump to the auxiliary equation already? M squared right? So m minus 2. Oh, this is m minus 2 squared. It's a repeating root. So what do we get? According to our solutions, we got y equals e to the 2x. Y equals, well, it's the same solution. Clearly, they're not linearly independent, right? So we can't repeat the same solution. So what do? We use a technique from last time to come up with a second solution. So we use a reduction technique that we just did. So this is the reason why we went through that first one first, when this is so much easier. That's what we want. We want a happy Alan. All right. Now there's another form. You can kind of guess what's going to happen here, right? Or can you? Can you guess what's going to happen here? So if we have this business over here, and then we try to solve for this, we're going to get imaginary numbers, right? But hey, wait, don't blow it. What? So this is an interesting dilemma. Before we answer this dilemma, I just wanted to take a look at these three examples, because these are the three cases that we could possibly run into. When you have a second order, when you have a quadratic equation, right? When you guys studied quadratic equations, remember there's three possible answers. One, you get two distinct real roots. The second one, you get one repeated real root. And then the third, you get two complex roots. Those complex roots happen to be complex conjugates. Complex conjugates. They have the same imaginary value except plus and minus. So those are the three things that we have to kind of cover to cover our basis here for these second order linear differential homogeneous differential equations with constant coefficients. Oh, this one?
Plus and minus.
For this, are you talking about this? No, let's hold off on that. Let's keep you in suspense. Oh, I don't have an explanation. That means I have to write it all up. All right, I guess I have to write it all up.
I think I write suspense in my notes.
Wow. What was I going to say? I think I was talking about some constant coefficients. So A y double prime plus B y prime plus C y equals 0. This has an auxiliary equation. And this has three different scenarios. Repeated. So there's three different scenarios here. We get two distinct real roots, then your roots are, let's say, R1 and R2. Let's use R. Then if your roots are R1, M is equal to R1 and R2, then your solution to the DE is going to be Y1 is going to be e to the R1x, and Y2 is going to be e to the R2x. That's pretty straightforward. The other scenario is that if you have a repeated root, which means it's a perfect square, you factor it, you get m minus r quantity squared. Then your solutions the first one is just going to be that power. The second one, and we kind of did this as an example, but you could do it in general as well, that if you just multiply that e to the x by x, or if you multiply e to the rx by x, then you're going to have a second solution that is going to be linearly independent from the first solution, and this will be your fundamental set. Now this last one is going to be a lot of fun, because we're going to get into complex numbers. So a complex conjugate means that your solution has the form a real number plus and minus a complex number times I, or another real number times I. So if you were to do the quadratic formula and you got that stuff in the square root to be negative, there's a plus and minus involved there, right? So the real part will be plus and minus, the real part would be the real part, and then you got the imaginary part that's plus and minus. So what we want to do is we want to think about our solution as that complex number times x, and that's going to be the power for your exponential function. Now when we're adding powers, you know, you can split that up with different bases and stuff. So you got e to the alpha times e to the beta I times x. So this is the big question that we have. We started with real numbers, and we want our solutions to be real numbers. Alpha x, thank you. Well, this would be y1, and then we'll see that this is going to split up to two different things. So this is where we take our little diversion. What's e to the beta I times x? Yeah, I might as well just tell you. I can't think up of a nice story. I was going to try to tell you a nice story about this, but oh well. So it turns out that this is equal to cosine beta x plus I times sine beta x. This oh, maybe. Oh, the mobs is when you raise it to a power. Yeah. Why don't we move him down here? Euler's already got a formula.
Just specifically the e to the pi I.
Yeah, e to the pi I. The e to the pi I is a special case of this.
I'm saying, is the Euler's identity just that one specifically, or is it this general guy?
Well, this Euler's formula is this general guy. Anyways, so the whole story behind this goes back to a complex plane, and a complex plane is where you get to write any complex number on a two-dimensional plane. because the complex number has an alpha and a beta, has two terms, and so you can write them up into, put them on a Cartesian coordinate. Actually, it'll look more like a polar coordinate. Anyways, this is just a formula that we should just remember or be able to look up. And the idea here is that yeah, we could do a lot of proofs with a lot of things, but let's get back to our task at hand here. We got e to the alpha plus I beta x. Then essentially it's just going to be this thing times e to the alpha and what we have here is that this is our potential y function. What we have here is that I is just, you know, it's an imaginary number, but it's really just a constant. And then what we come up with here without the I are two linearly independent solutions. So these two are linearly independent solutions to our differential equation. So what we can say here is that y1 is going to equal to e to the alpha x cosine beta x, and y2 is going to equal to e to the alpha x sine beta x. So if your auxiliary equation comes up with complex conjugates, then you can write your solution like this. No, see, the fact that this is a constant, when you piece it together with the superposition principle, you'll just say C1 and C2, and that's like your constant. So I tried to highlight this idea that I is just a number. I mean, it's complex. Yeah, I went back there and wrote it. So it's a complex number, but it's really still just this constant value. It's a constant number. So for complex solutions, your functions will look like this. So either your functions are e to the whatever power, or your function, if it's repeating, it's e to that power, and then your other one would be x times e to that power, and then your third scenario is when you have complex numbers, then your solutions are this. Okay? All right. Whew. That's a lot.
Why do you get to drop that as a constant, but so why do you get to drop out constants in these cases?
Because we have general solutions. When we write our general solutions, we're going to multiply it by C1 or C2.
Okay.
And then it'll just merge with that. Yeah.